Binary searching. We've already talked about linear searching, but we saw that was pretty slow with a large group of elements. It was of the order of n, the number of elements in the array. Here we have an improvement, but it only works on an array that is sorted beforehand. Let's follow through the idea. Here's an example of a sorted array. Let's suppose we're looking for 115. Here's what we can do. First of all, I've rewritten all the numbers here with the index that they have in the array on top. The indices go from 0 to 16, so the average, that means in the middle, is 8. Let's see what number is specifically at that position. It's 90. Now 90 is less than 115, and since this array is sorted, everything less than 90 is also less than 115, so the answer cannot be there. Nor was it equal to the point here in the middle, so all that is left is this part of the array. So that's what we focus on next time, just here. Notice that the largest index is the same, but we've moved the smallest index from 0 to be one more than where the middle was before. We can continue. So the minimum index is 9 and the maximum is 16, and the average with integer arithmetic comes out to be 12. So we look here. This time it's the other way around. That number is too big. So we can exclude all of these numbers, and the only numbers left to consider are here. So the maximum index is now shifted from 16, where it was before, to be one less than where the middle of the last interval was. This time around, it turns out that when we take the average of the low and the high indices, of course, in the middle is 10, and we're lucky enough to find 115 directly there, and so we're certainly done. And so it was found at position 10. You see how we chop the whole set of numbers to look at least in half each time. If we get down to 1, we've got our last thing to check, and we're done after that. We determined the position 10 in basically 3 steps, looking here, and then finding it here. We might have had to chop it down again if we were looking for like 114 or something. And if we'd been over in this section, it's longer than this section, and there could have been one more step. The maximum number of steps would be 5, and for other numbers, even if we had to go down to just a single number to find it, it would be 4 steps. And using logarithms, we can say that if we take this 17 and we look at its logarithm base 2, it's between 4 and 5. 2 to the 4th power is 16. And 4 and 5 are the largest numbers of steps that we could take. Let's look at this in the actual code. Here is our function int_array binary search. It takes an array that we call data again, and again we're searching for a value that we call item. Notice that we were keeping track of the range of indices that we had to deal with. We start off going from the smallest index to the maximum index here, where n is the length of the data. Then we do just what we did in the illustration above. We found the middle index by taking an average with integer division. And we check to see if we already found our item, in which case we're done, and that mid index is the one we want. If we didn't find it there, then there are two choices. Either our item was bigger than the value in the middle. It's the second reduction that we made, in which case we moved up the minimum to one past the middle. And the final possibility is that the item is smaller than the middle data, in which case we changed max and brought it down to one less than the middle index. And as long as we don't find it, we keep doing this and we keep chopping down the interval. We only need to do this as long as there is actually data to look at. And we will have a positive length interval if min is less than or equal to max. We could keep going down and not find it, and in fact we would end up with max actually being greater than min, and we'd stop. And if we stop without having returned a mid, it means we couldn't find it, and much like we did with string searching with the index of, we return -1 on impossible value for an index to indicate that we did not find what we were looking for. The whole code is in the binary searching project. Here's the main program. It's very much like the one for just the linear searching. The difference here is after you get data from the user, we use one of our sorts. Here we're using the shell sort to sort the data to make sure it's in order, which we need for the binary search, and then the rest is much like we had before with searching. Well, let's try it. Let's give it some data. There's a few numbers. Oh, and let's suppose we want to look for 80. This time, that's one that's not in the list. Let's see what happens. So it's giving us the array indices for the data sorted. And we see that the middle here was at the third place. 80 is certainly bigger than 7, so we look at this part of the array. The middle is then at index 5, and the data is still bigger, so we only look at the larger part. And at this point, it's not the only middle element, and so we have not found it. We could try something else. Let's go for 5. It's less than this 7 in the middle, so that means it must be in this range. And we find it on the second try. The middle here is in fact 5 at position 1. There is a lab later in the chapter to compare searching time.